Hiya, it's James again. We're going to do a video now on calculus differentiation, so describing a little bit about where the laws for calculus come from. So why calculus? Just briefly, for employment, further study, for engineering, or to understand and control things in the world around us. I won't go too much into it, but calculus is everywhere, so it's good to understand where it comes from and how it works. Real life applications to do with related rates of change like speed, distance, time, how things change in the engineering world. When is my chemical vat full? If it's filling up at a certain rate, when will it spill over and poison everything? Physics, can I take this bend at 50 miles an hour and not crash? Can I go through this angle in an aeroplane without the wings separating from the fuselage? And loads of things on simple harmonic motion and how pendulums and different sinusoidal functions work. So differentiation, that part of calculus, is comparing rates of change and seeing how things change. For instance, how a bath's water level changes as the tap's flow rate changes, if you like. And that's Isaac Newton, one of the forefathers of modern calculus. And some of the notation, in addition to the first video, if you've got an output y is the function of x, then the first derivative is called dy dx, or f prime of x, or y prime. Now there's something called the power rule, which pops up all the time. It's like one of the first rules you learn in calculus. And if you've got a function like an output y, which is like ax to the n, which could be like 3x squared or something like that, then the first derivative, or the rate of change of that function, is n times ax to the n minus 1, which is worth remembering, and we'll be proving why that is true today. So consider a function y equals x squared. It could be any function, but this is a nice one to start with. So you've got 2 points on the line, the two green circles there, a and b, like in the first video. The coordinates on any Cartesian plane are like x comma y coordinates, you know, the across amount and the up and down amount. So point A's coordinates are x, y, but remember for this example, because y is actually x squared, that's a function, then the y value is x squared. So that's why A's coordinates are x and x squared, which relate to x and y for this function of y equals x squared. The second point on the line, b, it also has coordinates of x, y, but its x value is a little bit further along from where a was, and the difference between the two we call h. So b's x coordinate is x plus h, and b's y coordinate is therefore the square of its x coordinate, because our function is y equals x squared. So b's y coordinate is x plus h squared. I'll just show them both together there. So they are the coordinates of points a and b, which will become quite important as we move b closer to a and h sort of disappears and becomes almost zero. Then we get the gradient of the tangent line, like in the first video, which is the first derivative of this function y equals x squared. So just think of any gradient or slope is like what we call the rise over the run. It's the change in y divided by the change in x. But when we get a little bit more technical, pretty much that's all it ever is, but we write it slightly differently. We call the dy dx is the first derivative, which is the change in y divided by the change in x. And to find how something's changed, you need to know what it is now compared to what it was then. So it's the change in y is the new y value minus the old y value, and the change in x is the new x value minus the old x value. And as the change in x approaches zero, we get what we call the derivative of a function. And just to make it look nice, we call the change in x, we call it h, just because then the algebra looks simpler. So the first derivative, f prime of x, or dy dx, which is how y changes as x changes, is the change in y divided by h. And that bottom equation down the bottom is the equation for finding derivatives. The derivative of a function is that basically, and all that is a change in y over the change in x. But what we say is, as the change in x, which we call h, goes really close towards zero, then that's what we call the first derivative. And what people often do to prove some of the laws of calculus differentiation is take a nice simple function like x squared like we had before, and using the equation we just saw, we're going to prove what the derivative of x squared is. So a's coordinates, like we said, were x and x squared, and b's coordinates for x and y is x plus h is the x coordinate, and x plus h all squared must be b's y coordinate. And taking the equation, the new take away the old, y divided by h, and what we've got there is x plus h squared, which if you do what we call a binomial expansion like a FOIL, first outer inner last, this is what we end up with. You get x squared plus h squared plus 2xh, that's the new value of y at point B, and the old value of y at point A is x squared. But as you can see, you've got x squared take away x squared, so that cancels down a bit, and then we've got on the right there h squared plus 2xh all over h, so you split that fraction up, which is h squared over h, and also 2xh over h. So on the second side, on the right hand side, the h's cancel, and from the definition of a derivative, as h, which is the change in x between points A and B, and as that goes to 0, we're left with 2x. So using that formula from earlier, we've proved that the first derivative of x squared is 2 times the value of x. So the slope of the curve y equals x squared is twice as big as whatever the value of x is at the time. And it looks like earlier that equation that we had, y equals ax to the n, we had x squared and it became 2x. So it looks as though it's going to be the form of n ax to the n minus 1, because we had an x squared and we ended up with just x to the 1, so we must have taken 1 off the power. And you can have a go yourself at trying to find out the derivative of x cubed, and the only thing that really changes is the expansion of the bracket of the new y coordinate for point B. So that brings us to the power rule that we've already really spoken about, and in the next video we're going to be doing some examples. But if your original function y is ax to the n, for instance 3 times x squared, then you bring the squared 2 down in front, which becomes 2 times 3x, and then you take 1 off the power, so 3x squared would become 6x to the 1, or 6x. And just to demonstrate how to do that, it's really easy. You know, calculus can be really simple. It's only like tying your shoelaces, just a few rules to follow. So if your function is ax to the n, as in a number times x squared, or a number times x to the power 4 or whatever, bring the power down and multiply by it, because now it's like a factor. It comes down in front and you multiply by it. And then don't forget to take 1 away from what the power was. So if you add x squared, it becomes x to the 2 minus 1, or x to the 1. If you add x to the power 4, it would become x cubed. So you take 1 off. And that is pretty much as hard as it gets. And we'll leave it there for now. We'll do some examples in the next video. And any questions or comments, please leave them below. Alright, thanks.